Hello and welcome back to the good stuff that we have been doing. Today in this video, we're going to find this series for this beautiful all-ice number E. And we're going to do this not with the calculus approach where you use Taylor series to find the series, no. Like Taylor's theorem, I mean. Here we're going to try to do this without calculus, just the normal binomial expression. And how do we go about this? Well, we're going to do it straight from the definition, because by definition, E actually is defined to be the limit as n runs to infinity of 1 plus 1 over n to the power of n. Now, of course, this is actually the same as the limit as n runs to 0 of 1 plus n over 1 over n, if you take n to be 1 over n, okay? But we're going to use this definition as well. Now, observe something here now, that this looks like something you see when you are doing compound interest. And actually, that is how this E came up, although E appears in many areas of mathematics, analysis, whatever. In fact, E is everywhere, even your torchlight, even in your food. Even when you sleep, E is always in your dream and looking at you. So E is something that does not need any introduction. It's just a beautiful constant. Everybody loves it. I don't know who doesn't love it. Everybody loves it. So we're going to try to do justice to E by getting a series without using calculus to it, okay? And we're going to do it straight from definition. And to do that, let's see. We're going to come and say, if you remember the Binomial Theorem, it says that 1 plus x to the n would be 1 plus nx plus n. Then you have an n minus 1 over 2 factorial x to the second power plus n minus 1, then n minus 2 over 3 factorial x to the third power. And you continue in this way. So this is the Binomial Theorem. So here we're going to use x as 1 over n. So this will be 1 plus n times 1 over n plus, then you have n minus 1 over 2 factorial, then you have a 1 over n to the second power, then you would have n minus 1, and then n minus 2 over 3 factorial, then you have an 1 over n to the third power. And then we can continue this way, and we'll end up with n minus 1, n minus 2, up until n minus r plus 1, all divided by r factorial. Then you will have a 1 over n to the r power. So of course this goes to infinity, but we only need to get the pattern before. We don't need to write out all the terms. We can't even write out all the terms because it goes to infinity. So we just have the pattern here. Now the first expression is just 1 plus 1. So we have recovered 2 terms from that series. Now what about the third one? Where notice here that at the top you can factor an n squared out. So if you factor an n squared, you would have something like 1 plus 1 over n, I think so, yeah. 1 plus 1 over n. No, minus 1 minus 1 over n. So, although it doesn't even matter if it is a minus, so, but let's just write it as it is. We'll write it this way because it will be an n squared minus n, yeah. So, at the bottom, we have a 2 factorial. Then you have a 1 over n to the second power. Or we could just write it as 1 over n squared, so because we can easily cancel out. Then you have at this part, you can factor out n cubed, then you have n minus 1 over n. No, not n. You have 1 minus 1 over n on the first bracket, and in the second bracket, you have a 1 minus 2 over n squared, right? N cubed. Because if you multiply this out, you have a n. If you factor out n cubed out, this is 1 over n squared, yes, and then this is 2 over n squared. Let me just multiply and see the pattern. So you have an n squared minus n, and you're multiplying this by n minus 2. So you have an n cubed minus 2n squared minus n squared plus 2n. So you have an n cubed minus 3, okay, minus n cubed minus 2n squared minus n squared, okay, minus 3n squared plus 2n. So if you have factored out an n cubed, you have a 1 minus 3 over n plus 2 over n squared. Okay, so we're going to have at some point 2 over n squared. Yes, I think I should be correct on this. Let's just keep it this way. It doesn't even matter whatever form. It will always be in case of 1 over n, 2 over n squared. So it doesn't matter how we arrange it. As long as we keep a 1 here, we should be in good shape. So this is divided by 3 factorial. Then you have a 1 over n to the third power. Okay, I'll just write it as 1 over n cubed. So we have a 1 over n to the third power. Then we would have, okay, let's go up so we can get the general pattern here. Then you have a plus, okay, dot. This over here right now, what we'll have here is, okay, we should be having the n to the r power for sure. Then you have a 1 minus 1 over n to the r, n to the, just write 1 over n. Then you have 1 minus 2 over n squared. Then you would have 1 minus 3 over n cubed. Then plus, then you would end up with 1 minus r minus 1. Okay, how do we take care of the r? It should be 1 r minus 1 over n to the r. Yeah, this setup should work. So you divide it by r factorial 1 over n to the r. Again, it doesn't matter how we write it at the top there, everything is going to still cancel out at the end. Then we'll divide. We are going to cancel some things, so we're going to cancel this out. We cancel n squared here, n cubed here, and so on. So we're going to end up with 1 plus 1 minus 1 over n over 2 factorial. Okay, plus 1 minus 1 over n and 1 minus 2 over n over 3 factorial, plus we have 1 minus 1 over n, 1 minus 2 over n, and 1 minus 3 over n. Then you would have divided by 4 factorial plus up until infinity. So essentially E, which is the limit as n tends to infinity of 1 plus 1 over n to the n power, would be equals to, if you take the limit as n tends to infinity, everything here will vanish. So you have a 1 plus 1 over, okay, there's a 1 here. So you have a 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial. So this is plus 1 over 5 factorial. So this is how we get the limit for E. Okay, just by the binomial theorem, by simply taking the definition of the binomial theorem. So that is that. Thank you for watching this video. Please do subscribe to the channel. Bye.